So, hello everyone, welcome. Welcome to the Galgali College of Engineering graduate student community Fall 2024 seminar series. Today we have Kuntal Maity. So first, let's take a look at our GSC leadership team for the academic year 2024-25. So we have Rodney and Rachel who are the co-chairs of the GSC leadership team. Then publicity is handled by Swapnil and I. We have Siavash as the treasurer, and we have a very large support team uh, in which we have Louis, Roshan, Samuel, Mohammed, Jason, Himadri, and Ryan. And all this leadership works under the guidance of our faculty mentor, Farooq Mistry. We have our uh, regular meetings on Thursdays at 4:30 p.m. These meetings are held in person and at the Dave and Susan Bird team room. So if anyone would like to join these regular meetings, you are most welcome. For the contact, please contact Rachel and Rodney. Their emails are here, and the time we keep for our regular meetings can be adjusted according to everyone's availability. I hope everyone here, or at least at OU here, follow or are a member of GSC on Engage. If not, you can join the GSC at GCOE Engage page by scanning this QR code. Okay. We also have a LinkedIn page in which we keep all up to date of our events and the progress everyone is here making. So you can follow our LinkedIn page as well. You can just scan this QR code. Also, we have a Facebook page in which all our social events and any other type of events we all post it there. So you can follow us on there. So again, the QR code is here. In our GSC, we do have our YouTube page where we post all of our seminar series recordings, which we have access to. So in case you are curious about any other previous seminar videos, you can check it out on our YouTube page. Um, we have our Dave and Susan Bird team room, which the leadership team uses for its regular meetings, as well as it's a place just to hang out and, catch up with your work or anything, or even relax. So we have some basic amenities in this room, like couches, whiteboard, coffee pot, microwave. So if you would like to have an access to this room, do join us and become a part of our leadership team. And through your email, we can provide you the access. Just a reminder during the seminar talk, and in the chat, we will be providing a sign-in sheet Google form link. So please do fill that up. It helps us keeping a track of all the attendance. So with further ado, today we have Dr. Kuntal Maity. He is an instructor and postdoctoral research associate in the School of Aerospace and Mechanical Engineering at the University of Oklahoma. Today he will be giving a talk on powering the future, clean energy and healthcare. So without further ado, uh, the stage is yours, Dr. Kuntal. Yeah.
Thank you. Thank you, Avinash and Farooq and all the GSC members. Can I share my screen now?
Yes.
Okay. Okay. So is it visible now?
Yes, go ahead.
Okay. Thank you so much. And so myself, Kuntal Maity, I am postdoctoral research associate in the School of Aerospace and Mechanical Engineering. Since 2021, I am working with Dr. Minal Saha in the hybrid composite lab for advanced multifunctional materials. Uh, First of all, I am very grateful to Dr. Saha that he is supporting me throughout this year, and also our AME department. Particularly our departmental chair, Dr. Partho Sarathi. So, and yeah, thank you everyone for attending today's talk and giving your attention. So today I'm going to talk about powering the future, that is clean energy and healthcare. So let me start with that. Nowadays, we all are using smart electronics devices like smartphone, smartwatch, and but also on the other hand, a lot of biomedical devices. For example, uh, patient with cardiac problem, they use pacemaker. They have that pacemaker also has battery, and that heavily relying on the lifetime of the battery. So there is a question that wouldn't it be great if we could power up these devices by themselves or self-power? So this is the today's research theme of my talk, and let's see. Before that, let me tell you about my background. I'm originally from Calcutta, India, a beautiful city. So Calcutta is also known as City of Joy. And interestingly, Calcutta was the then capital of India until 1911. So a lot of historical things. So my early career started at Calcutta, my education. So I did my PhD in Jadavpur University, which is in Calcutta. So my research mainly focused on material science, and which has a lot of application in energy and healthcare. Well, during my PhD, I was supported by full funded fellowship from UGC Government of India. I greatly acknowledge that. I actually qualified that national eligibility test, so which is one of the India's most prestigious fellowship. So I greatly acknowledge the support from Government of India. So this is one of my old photos from Jadavpur days, and my advisor, Dr. Mondal, he also joined. So my interest for the research started during my early days in Jadavpur. So Dr. Mondal very motivated me for the research, and of course for the postdoctoral research. And he currently is moved to INST, which is in Mohali, India, one DST institute. And a lot of folks from India today joined. Thank you so much for joining today. And we have also collaborator. I must have to acknowledge that from Germany, that Dr. Smeisar and Dr. Carsten Henkel, they are the lovely people to working with them. And we got a lot of support from them. So I acknowledge their support. So now let's talk about the clean energy and the nanogenerator. So I already mentioned that there are a lot of smart electronics devices we are currently using, but we are worried about the charge of this battery. So if we could power up these devices by themselves, so there is huge demand in self-powered system, battery-free self-powered system. So one of the solution is nanogenerator. So nanogenerators are first developed using the piezoelectric material for converting high entropy energy into electricity. So if we look at the first law of thermodynamics, that energy can't be created or destroyed. Energy is only transferred from one form to another form. So like fossil energy, that is actually converted into heat and wind and other mechanical energy. So in our surroundings, lot of mechanical energies and thermal energies available that we typically waste, be it water wave, wind vibration, breeze oscillation, raindrop, everything. So even human walking or running, those are also involved with a lot of mechanical energies. So that's the challenge, that if we could use that uh, waste energy into electricity. So from the second law of thermodynamics, which can be understood by that, of course, the entropy is increasing always. The highly concentrated quality fossil fuels energy is actually dissipated into heat and mechanical energy. So now challenge is how that low quality or unusable energy can be used to reusable energy. So that is the challenge, and nanogenerator is capable converting that high entropy energy into usable electric power. And we believe that in the future, so not only the fossil energy, but also that nanogenerator or high entropy based energy will dominate the world. So now let's look at the fundamental physics of the nanogenerator. So this is the famous equation of Maxwell's electricity and magnetism. So those are the four fundamental equations. Those are the basic of today's world. So without electricity and magnetism, we can't think. So first discovered James Maxwell. And if you look at the fourth equation, that is the Ampere's law, and there is the Maxwell's addition, that is displacement current, del D by del T. So the first term, del E by del T, that gives birth of the electromagnetic wave, which is foundation of wireless communication, radar, and later information technology. Interestingly, the second term, that is del P by del T, which is directly related to the output electric current of the nanogenerator, which is basically the polarization induced current. So which relying on the material's spontaneous property or inherent property. So we can say that nanogenerators are basically the applications of Maxwell's displacement current in energy and sensor. So piezoelectricity was discovered in 1880 by Curie brothers, but it was not until
Dr.
when...
Maity,
Yes.
sorry to interrupt. There's a gray block across the top of your slide that's blocking some of your information. I think it might be the view of the other people in the Zoom meeting. Yeah, right there. Sorry, there were a couple posts in the chat about it, people not being able to see. I think if you minimize the view of other people, it'll clear it up.
Minimize the view, sorry?
Yeah, right where your mouse is, all we see is a gray block right there.
Yeah.
And it was covering up some of the figures that you were showing.
Okay, so what should I do?
I think let's minimize and again maximize the slideshow.
Okay, let me stop sharing and share again. Is it okay now?
There is, yeah,
Yeah,
now
perfect.
Okay,
perfect.
okay, thank you.
Thank you.
Yeah, thank you. Sorry for interrupting.
Yeah, you're good. So first piezoelectric nanogenerator was published that reported on the zinc oxide nanowire arrays. It was discovered by Professor Jedel Wang and his student J. Song from Georgia Tech. And the phenomenal work actually published in Science in 2006. So they actually discovered that when zinc oxide nanowire arrays over here, that is deflected by the mechanical tip during the conducting atomic force microscopy, they found some nanocurrent over there. So that they reported as the piezoelectric nanogenerator. and published in Science in 2006. After that, you see that tremendous research has been carried out on the nanogenerator, and this is the a graph for the number of articles throughout the year, and it's exponentially increasing, and it's very interesting to see that people are getting motivated and interested. So a lot of ideas like idea is that the nanogenerator can be placed like human walking. We use shoes. We can insert that nanogenerator into us insole. And while walking, we actually imparting some pressure. So from that mechanical energy, we can also generate some electrical power. And now let's talk about the healthcare. So for example, cardiac diseases, brain diseases, or cancers that affect millions of families around the world. In United States, CVD actually causes 1 in 5 deaths. And also respiratory diseases, which is related to the lungs disorder and the pulmonary lungs disorder. So that also very affecting our people's health. But the current health status and the diagnosis of diseases still relying on the hospital-based diagnosis. So, and the traditional methods, for example, X-ray, we do X-ray for the lungs, right? So that image may not be perfect. So it always relying on the observation of that clinicians. So can we avoid that kind of thing? So another thing that for real-time health monitoring and therapy, lot of commercial sensors and implantable medical electronics, those are relying on external power. Like I said, that pacemaker has also the battery. So if battery dies, then the patient needs to make the surgery. So which is very critical as well as expensive as well. So that's why nanogenerator or this kind of wearable sensor can be effective to detect the diseases in early stage. And importantly, 50% of the death can be prevented if early detection and intervention is possible. So now let me talk about the piezoelectricity and piezoelectric materials. So like I told that piezoelectricity is relying on the mechanical energy. So the piezoelectric material basically has non-centrosymmetric crystal structure. So when there is some load on it, so there is some charges, the electrons are accumulated in one side and positive charges accumulated on other side. So, and if we connect with external wire, then according to the mechanical load, we can get the electrical energy. So there is some polarization arising across the material. So a lot of piezoelectric materials like quartz, salt, and some ceramics. A lot of ceramic materials are, you may know, like barium titanate, PZT, ZNS. But those inorganic piezoelectric materials are limited because they are toxic in nature and brittle and may not be compatible with biomedical applications. So people are tending towards the organic material, piezoelectric organic materials, or maybe natural materials. Those are originated from the biological system itself and promising because they are biocompatible, flexible, and mostly biodegradable. So like piezoelectric sensor can convert any kind of mechanical energy into electricity. So we can make a sensor, and you see that here, that arterial blood pressure. So if we place the sensor on the wrist, that pressure, blood pressure can give the mechanical load, and that sensor can actually detect. So we can use the piezoelectric wearable sensor in the regular monitoring of our heart pulse. Also, piezoelectric biomaterials can be found in different applications like cancer treatment or tissue regeneration or implantable devices, neurological treatment, and voice monitoring. So we envision that there would be a system or platform based on the novel biomaterial or biocompatible material, which can be used for the disease diagnosis, health assessment, or as well as the treatment to fill the research gap. so that we are dreaming of the personalized healthcare system. Suppose someone in a remote place or is in village, so he needs some urgent medical attention. So there would be some system that wearable sensor can be connected to the Wi-Fi or IoT, and that IoT will give the information to the medical team or system or whatever. So that's how we envision that we can bring and you can use that piezoelectric material based nanogenerator or sensor can change the healthcare system. So one of the biocompatible piezoelectric polymers we are using, that is PVDF. I started working with PVDF during my PhD days. So this is basically consisting of CH2CF2, and it is very lightweight, flexible, non-toxic, and low-cost material. Interestingly, PVDF has a lot of phases like alpha phase and beta phase. And alpha phase is basically non-polar and beta phase is polar. So to get the piezoelectric advancement, we need that beta phase. So all CH2CF2 should be aligned in one direction. So there are a lot of techniques available to change the phase from alpha to beta. One of the interesting technique is electrospinning technique. So by electrospinning technique, we are using that there is a syringe and polymer solution should be inside and high voltage should be applied. And there is a collector which is grounded. So mechanical stretching and the electric pulling both simultaneously can take place by this electrospinning technique, and we can convert the phase from alpha to beta. And interestingly, we can get the nanofiber out of that electrospinning technique. So that electrospinning technique that we also recently acquired in our lab at Felger Hall. So I have some videos, let me show you. So this is the syringe, and there is some that spinning is happening and the fibers are collected on the collector. So this is basically multiple spinning, and one advantage that by this technique, we can get large area nanofiber mat. And if we look at the microscope, that fibers are actually nanometer range. The diameters are in the nanometer range. So here you see that mostly around 100 nanometers fibers, and we can tune the area. So where other techniques, those are constant with the large area fabrication, that electrospinning technique comes up with a new idea that we can get large area. And these fibers are very flexible, air permeable, and we can twist, roll and fold. So let's see the application of nanofiber waves in different sector. So a lot of applications like in defense and security, healthcare, tissue engineering, and drug delivery, also environmental engineering, and as a membrane or filter, that nanofiber has a lot of application. So we are mainly interested about energy, making the sensor in our work. So this is today's objective. The objective of my today's talk is highlighting the potential of advanced material and smart technologies in sustainable energy based on piezoelectric, pyroelectric, and flexoelectric system. And another objective of my today's talk is showcasing the scalable real-time solutions for health monitoring and environmental sustainability. So one of the work I want to highlight that I did, that is very important work that I did during my PhD, that this nanofibers, one of the problem is that making the electrode, because those fibers are air permeable, so there is porosity. So any kind of deposition technique may not be feasible to make the electrode. So I come up with an approach, that all organic approach for the fabrication of nanogenerator out of that nanofiber. So let's see that first we did electrospinning and we get different layers like 1, 2, 3. The first and third layer should be coated by the conducting polymer, that is E dot. So here's the example that after coating, that fibers this P dot is actually conducting polymer. And this, after vapor phase polymerization, that is VPP, that fibers are coated by conducting polymer. And at the microscope, we can see that evidence. So this is the typical methodology. I'm not going into the details. So finally, after getting that fiber and making the electrode, we encapsulated with soft polymer matrix, and this is the device we fabricated. And here is the practical application, that when you are applying the pressure and release by simple finger touch, it can generate the voltage. And not only that, we also used that nanogenerator in household application like kitchen blender. We attached our sensor on the kitchen blender, and for the vibration on and off, there is some voltage response. And we also used one example, very funny, that we placed the nanogenerator on a toy, and with the drum beats of the toy, that can generate the voltage. I have a video. Let me know whether it works. Yeah. So you can see that when that toy, there is the drum beats of the toy, that nanogenerator is capable of generating the voltage, and we can measure from the oscilloscope. This is very cool that we can generate the electric power from any kind of mechanical vibrations or source. Also, we have also demonstrated the mobile vibration related output response, and we also lit up some LED lights. Not only that, so I told about that it can generate, if you work, it can generate the power. So if we work on that, this is the power generation from the nano generator, that when we are working, that it's generating the voltage. Of course, for different people, different weight, and the power generation should be different. So we can use it for weight measurement mapping application. So what we did with different weight people, they actually worked, and we can actually map by the use of principal component analysis, and we were able to map different weight person by using that nanogenerator as well as sensor. And this work actually published in ACS, and I was the lead author, and currently cited over the 130 times. And another work, we explored that PVDF-based electrospun nanofiber-based nanogenerator can generate that LED. So here is some video. Just you can see that simple touch and release can generate the power, and that power is capable to lit up the LED. And here you see that there is no external batteries connected, and the LED is lit up by only using a nanogenerator and simply imparting the pressure, finger touch. So we have also lit up not only blue LEDs, also green LEDs, and the LCD screen also we were able to lit up. Another application, interesting application we explored, that speech signal recognition, like different alphabets, A, B, C, D, E. For different alphabets, you see that different pattern. And if we further analyze by first Fourier transform, that FFT, so we can get the resonance frequencies different. And for different musical instruments like piano, violin, and flute, the sensor response is different. So we can say that it can be used for signal recognition purpose as a sensor. And this work was also published in a Wiley journal, and I was the lead author in that article. So now let me talk about the sustainable piezoelectric materials and additive manufacturing technique. So this is the work I started coming over here. So I told about the natural piezoelectric material. So cellulose is one of the natural piezoelectric material which is mostly available and totally biodegradable polymer on the earth. And it is endlessly available in various plants and woods consisting of microfibrils. But challenges is the design and fabrication of nanogenerator. How can we make it ultra sensitive, or how can make the device? So we are adopting additive manufacturing technique in this case. So additive manufacturing, you know, that is recently becomes an emerging technique which can fabricate complex structure and macroscopic shape with controlled microstructure. So this is the typical scheme of the additive manufacturing technique where you have to first design the code and you put into the printer control board, and you have the ink that you need to print, and here is the syringe, and you can put over here, and that according to your design it can print accordingly. But challenge over here in 3D printing or additive manufacturing, the formulation of viscoelastic ink. So because that ink basically needs to sustain a certain rheological property, like water it flows, but that ink should be like a paste, or I can say that peanut butter, it has some certain viscosity or rheological property. So here we designed our ink by adding elastomeric polymer PDMS with the cellulose, and we prepare two types of ink, and here you can see that 3D printable that paste that we prepare, and we also measured the corresponding rheological property by using rheometer. Here are the results. I'm not going into the details. So you see that viscosity also is greater than 0, and which is not like water. So that means that we can print our ink readily. And here are the structures, 3D printed structures. You can see that here, that is one of the interesting structure of our OU logo. And this is the microstructure. So interestingly, these microstructures are not possible by this traditional molding process. So for this, to make this 3D printing structure, first we have to make design, CAD design in the SolidWorks. Then by the help of slicer and repeater hose, we can prepare the G code, and after making the ink, we can print this kind of structure. So now we are trying to design and fabricate all 3D printed nanogenerator, but key challenges again the electrodes, the compatibility of the active material and the electrode to get stable and reliable device performance. So in this case, we have come up with an all 3D printed approach where electrode and the active material both can be printed readily. So this is the corresponding CAD model that layer 1, layer 2, and layer 3 all are printed, all 3D printed. So this is the layer 1 is the electrode, layer 2 is the active component, and layer 3 again the electrode. So by this technique, we can eliminate the electrode attachment issue and reduce the number of processing steps and equipment required during the fabrication of multi-layer device. So additive manufacturing can streamline design and fabrication of nanogenerator. So in this work, we have actually showed how effectively we can design and fabricate the nanogenerator. So those are the surface morphological investigation. I'm not going into the details, and mechanical testing, and there are some material characterization, chemical structure of the CNC. So now coming to the application, that here we explore pyroelectric thermal energy harvesting of that nanogenerator. Like I said, that piezoelectric material can generate any kind of mechanical and thermal energy into electricity. So if there is some thermal fluctuation, so it can also generate the polarization and in turn the electricity. So in contrast to the thermoelectric generator actually relies on the temperature gradient. So sometimes the temperature gradients are hard to realize, but piezoelectric material-based nanogenerator or pyroelectric material-based nanogenerator can generate the electricity by when the temperature fluctuation even of the human body temperature. So interesting thing is that this pyroelectric nanogenerator or piezoelectric nanogenerator can be used as a wearable skin sensor which can monitor our human body temperature. So to characterize that, we have set up a lab scale setup in our lab for this pyroelectric energy harvesting system. And this is the typical setup, that there is some lamp, heat lamp, which is actually controlled by microcontroller. There is a script in MATLAB, and we actually doing on and off of that heat lamp. So when on and off, the temperature is changing inside the chamber. So that pyroelectric material, or that piezoelectric material, is experiencing the temperature change, and it can generate the electricity accordingly. So we actually changed with different frequency, and changing the frequency, and you see that this is the change in temperature that nanogenerator is experiencing. And this is the corresponding voltage results with different frequency that nanogenerator is actually stored. And you see that is the interesting result, that with the change in temperature, that voltage is actually increasing. And here's another interesting result, that the thermal energy, pyroelectric thermal energy, we can store in a capacitor. So here we used different capacitor to store the energy. And you see that it's while cooling and heating, that pyroelectric thermal energy is stored up to 5 or 6 volt. So in future, or that energy can be used to power up smart electronics devices. That is our idea. So here also we demonstrated that the mechanical energy harvesting capability, so that nanogenerator, all 3D printed nanogenerator, when we are giving pressure, touch and release, that actually generating the power. So with different pressure, that generates different power. So next, we also demonstrated the biosensor capability. So like I said, that it can be used to measure our radial pulse. So simply we put this nanogenerator or sensor on our wrist pulse. So there is a tiny pressure over here that is sensor is experiencing. This is very tricky and challenging to get that tiny response. But by this design and fabrication, we were able to capture this signal. This is the typical heart pulse signal, and if we look at one signal, this is nothing but a systolic and diastolic pressure. So we can define ASPT and different wave of that heart pulse. So by using our sensor or nanogenerator, we can actually measure or capture the heart pulse signal. And if we further analyze that, we can get the frequency. And here is this is the 1.2 hertz frequency that is typically for a healthy human. This is the typical frequency. So next, we also demonstrated its application in cell power respiratory measurement. So while breathing in and out, our abdomen actually retracts and expands. So when we are before exercise, actually normal condition, we attached our sensor on our body, and we see that the response before exercise and after exercise is changing. So, and if we look at one signal, so this is the typical response, that it's increasing during the expiration and it's decreasing during the inspiration. And if we analyze that, this is the typical important parameters, FEV1 and FVC, that indicates the respiratory information of your health. And if you go to clinic, they do the spirometry measurement. So this spirometry measurement, we can get that information, same information from over here. And like I said, that after exercise, this signal has been changed. So our sensor is actually capable to detect the changes very effectively. And this is further analysis by doing fast Fourier transform. And by doing that, we can get a lot of information of our health, of our cardiac health, as well as lungs health. And this paper actually last year we published in ACS Applied, and it's good to see that it's currently cited over 45 times. And I was the lead author in this article. So now let me talk about another work, interesting work that I explored in our lab at Felgar, that composite materials and structural health monitoring application. Composite materials are very effective in different applications like civil or aerospace industry, like Boeing 787, that 50% of that aircraft is actually using the composite material. But why composite material? Because those are lightweight and high strength and stiffness and fatigue resistance. So our idea is that if there is some problem with that composite structure that it can damage. So our idea is that if we could detect the damage of that structure by our sensor, so our sensor would be cell power, ultra sensitive, and flexible and conformable. So structural health monitoring is very crucial for the aircraft structure or civil infrastructure. So by using our sensor, we are aiming to get all those information readily. So typically, the traditional sensors are used in structural health monitoring. They actually lack the flexibility and the shape adaptability and the sensitivity. Also, they need the external power. So that's our idea, that if we could use the 3D printed flexible sensor. In this case, we are actually looking to another important material, that is flexoelectric material and its corresponding response. So flexoelectricity is another interesting phenomena, that it also generates electric polarization when there is some strain gradient. So you don't need, it is like that if there is some strain gradient, bending, stretching, so it can generate the polarization as well as the electricity. By using this phenomena, we actually printed the flexoelectric sensor, and here are some examples. Like we printed two types of sensors, one 100% solid and one that with 50% infill, by using very simple material, elastomeric polymer PDMS. And here we tested our sensor with mechanical testing with uniform load. And here we see that the cellular, that is the 50% cellular sensor, is giving higher response. So later, we used that cellular sensor in our structural health monitoring application. So this is the carbon fiber epoxy based composite sample. So what we did, we made a defect intentionally for this characterization inside the composite material, and this is the defective area and this is the non-defective area. So we placed our sensor over the defective area as well as non-defective area, and we used the ultrasound transmitter and we get the signal. So it is very interesting to see that from the non-defective area, the average current response is 132, where from the defective area, current response is higher. So it means that we can distinguish the sensor response from different location, that based on the defective area to non-defective area. So these flexoelectric sensors, that's why, can efficiently detect defects and can be used for structural health monitoring application. So another application we also explored, that in situ damage detection while doing mechanical testing. So for this purpose, we attached our sensor on the composite sample and we stressed it. And very interesting result is that here you see that when it becomes the catastrophic failure, so the sensor is able to detect that signal. And also that tiny signal also captured by our sensor. So we can say that it is also capable in situ damage detection. So this work actually recently we presented American Society for Composite this year, and I was also the lead author in this article. And besides, there are a lot of projects in our lab. I am also one of our PhD students working on that, making the lightweight composite structure by using advanced manufacturing technique, which has a lot of application in aerospace and civil infrastructure and also the automotive industry. So yeah, these are also one of a plastic-based 3D printing technique, our undergraduate students, they also involved. I also mentored them in those projects. Besides, I also assisted in grant writing. One of the project proposal, we got the internal funding to acquire the electrospinning system. And thanks to OU VPRP office that for the funding that we able to get that electrospinning machine. And also we welcome others. If you are interested in electrospinning nanofiber, please reach out to us. We will be happy to collaborate and work together. And recently, we also in this year we also selected as an innovator for the Oklahoma BioStart program for biotech innovation. And I also helped in a lot of grant proposals. One is submitted in NSF and Naval Airfare Center. I'm also currently as a guest editor in Frontiers for the nano energy section, and also in the machine for the MDPI. So this is very interesting opportunity for you all. If you are interested in publishing paper, please reach out to us and we can work together for publishing paper. So I believe that, yeah, research and mentorship should extend beyond our classroom and lab spaces. And I actively engage with the Sooner Racing team. They mainly run by our undergraduate students. They are very interesting people, and I always try to help them and motivate them into the research. And I also served for the Oklahoma City Community Service in the big event organized by OU. So here's my Google Scholar, and if you are interested in those papers, please look at my Google Scholar, and those are the papers where I contributed. And feel free to reach out to me if you have any questions. So in summary, so we have explored the convergence of clean energy and healthcare technology by the self-powered device like nanogenerator and biosensors, and also highlighted advanced materials like piezoelectric, pyroelectric, and flexoelectric system, which can enable the renewable energy harvesting and power diagnostic tools. We also demonstrated scalable solutions for real-time health monitoring application from human health to aerospace structural monitoring, and emphasized that sustainable environmental friendly practices. So in future, also we are looking for sustainable material and advanced human health care, which can generate, detect our disease, and not only detect the disease, also in the treatment. There are a lot of implantable electronics application currently going on, and in future we are targeting to achieve that. And also the artificial intelligence. So by combining the AI, we can get the prediction very easily and at early stage. So we are also looking for to integrate the AI, with our sensor to get those information. Similarly, the structural health monitoring in advanced structural healthcare. So we envision that to make a smart structure which can generate the energy from the structural vibration, as well as we can detect the damage. So if damage detects the location and the damage severity, and if we could detect the damages at early stage, so we can save a lot of things. Also, another application we are looking for that nowadays we are talking about hydrogen gas, but those current techniques all involved with carbon-based material. So those in turn actually producing a lot of carbon dioxide in our environment. So this is very warning that CO2 is making the global warming and climate change. So our idea is that using nanogenerator and using high entropy energy to the reusable energy, we can split the water and we can generate the hydrogen. So this is we are looking for, and also carbon dioxide capture might be another significant research that we can look for. So in conclusion, that advanced material and smart design can address the growing energy and healthcare challenges. and it can impact a lot of application. So development of nanogenerators and biosensors can pave the way for renewable and scalable system to support our energy needs and healthcare capabilities. And in future direction, that advancement in material science and collaboration and smart design will drive the innovation and our societal needs. So we hope that this technology can impact very greatly and shaping our future for clean energy and healthcare technology. And yeah, we are open to connect, and thank you everyone for your kind attention. And I truly appreciate for your attention and coming to this talk. Thank you.
Thank you, Kuntal. That was, yeah, the research you are doing is quite intriguing. So at this time, we open the floor for questions if anyone has any questions to ask.
I have a quick question. Do you know, or have you done any research into the lifespan of the material you're developing? Like if it were to be implanted, how long would it last?
Yeah, that's a great question. That the durability is the it's challenging issue that we couple of experiment we did, but not it's great. But like after 1 month or after 3 months, how the response is changing or how's the material's lifetime that we are trying to do, but it takes time. So
Right.
yeah, that's a great question. That it's very vital for long-term application. Yeah. Thank you.
Thank you. I really like your talk. Thanks.
Thank you.
Thanks, Rodney. Does anyone else have any questions?
May I?
Yeah.
Yeah, it's a very interesting presentation and a lot of work actually. It's some of it is actually unbelievable that it can be realized. So wish you all the best. I have a question about because I have several applications in mind already. Like there's a lot of scope because I work in the area of oral appliances in which we have the problem in putting a battery inside the mouth. I will not go into the detail of what an oral appliance is, but there are different type of devices which are worn on the teeth, on natural teeth and on dentures and all. So there, it's very interesting that you say that just by touching, electricity can be generated. So my question is that if there is some sort of battery there and you have to recharge the battery by this touch, like for example, our tongue is continuously moving, even sleep, and even the jaws and mouth is moving. So have you done some work to see how this tapping, harvesting of energy can be done in vivo, like inside the mouth, for example, or in some part, like you have presented a lot of things, like cardiac and all that. So is it possible to charge a battery, for example, using this sort of technique, or it has to be totally a piezoelectric because maybe storage, I'm asking about the storage. So maybe we can talk about a specific application, but just, for the sake of all the audience, maybe you can give some example of what can be possible. Thank you.
Yeah, that's a great question. And that, in vivo application, we currently don't do over here, but a couple of groups like in MIT, they actually able to do the implantable electronics, like pacemaker. I told you that they actually make the pacemaker with make of piezoelectric material, and they don't need battery, and they are currently working on those implantable electronics. So we need a lot of collaboration as well with the biomedical people, those also to collaborate those in vivo application. And one important thing that today's talk, my emphasis on that sustainable material. So we are still currently using a lot of ceramic or toxic materials for human health application. Particularly, we need biomaterials or sustainable material, and flexibility is very important when you are attaching on the skin or inside on the heart, right? So flexibility, compatibility, a lot of issues come. So we need some flexible and biocompatible material in that case. So that's why my talk also emphasizes on the sustainable material. So we are focusing on more sustainable material, biomaterial in that sense, that which might be flexible, which might not be toxic, good for our human health. So that research, fundamental research is still going on. We need to collaborate with biomedical people. Yeah, we don't do, but a couple of groups are currently doing. And like, for example, that pacemaker, they able to do that. And they did it. Yeah. And implantable electronics might be very interesting topic that like smart pill, piezoelectric material with smart pill. You just eat it and it goes inside your into your intestine, and that inside your intestine, that information will give you wirelessly. So there would be like a lot of electronics should be also involved. So these are the cutting edge research currently going on, but not too many people, I would say, very less people. We need a lot of people to work on that, and fundamental research as well as collaboration, electronics, biomedical. This is like an interdisciplinary zone. Like biomedical people need it, biology and the electronics, physics, material science, all we need to work together to make it as a big. Thank you. Thank you
And
for
all the
asking.
best.
Yes, yes.
Thank you. Does anyone have any other questions?
Yeah, thank you, Kuntal, for a nice talk. Particularly, I like, yeah, most of the talk. I particularly like piezoelectric and pyroelectric stuff, but then the new work, particularly healthcare monitoring, right, on the based on 3D printing. So in precisely in page number 48, I've seen different colors. In your 3D printed objects. So, can you explain? I mean, what are the materials very briefly?
Oh, yeah. That three, yeah, that's a good question. That uh,
You just say the name. That's all. I mean, just go to
yes,
48 and say
48,
the
right?
materials. Yeah.
Yeah.
Some are black, some are white. So I'm worried. I mean, what kind of materials they are basically?
Yeah. So, those are, let me tell you that those are, one is cellulose inserted into the elastomeric polymer matrix PDMS, and a black one is actually the cellulose elastomeric polymer PDMS and the CNT. So that with the
Okay.
CNT that we used as an electrode,
I
and
see.
in the middle, the white one is the active piezoelectric material only with cellulose.
I see.
So top and bottom we printed with that conducting paste, conducting ink, and in the middle only without conducting that material, that is with cellulose. So that's how we are trying to say that all 3D printed approach, first print the electrode layer, the active layer, and the top electrode layer. All should be done in one shot.
On go, yeah. So,
Yeah.
and in the resulting materials, do you think is it flexible enough, like a piezoelectric stuff, what you deal with a PVDA, or the
Yes, flexible,
flexibility?
because PDMS is consisting of PDMS. That's a good question, that it's consisting of PDMS. So PDMS, you know that it's flexible elastomeric material. So it's basically flexible. Yeah.
Mhm. Yeah, and I like your acoustic work, particularly this is my comment that I mean, like you can show the where exactly you are placing your device. So in order to track the acoustics signals in your presentation slide, so that you can reach to the audience where exactly you are inserting it. And then because
Right.
the acoustic could have very big application in healthcare monitoring as well as the smart what is called like detection and national security. So that's the very good area you have shown very nicely. So with this, yeah, thank you again. Yeah,
Thank you.
and have a nice. Yeah, particularly you should do more work on the structural health monitoring. That shows showing very interesting results, particularly the tiny sensitivity to detect the several defects.
Right.
It's really a new piece of work. I really
Right.
Yeah.
It has a lot of application in aerospace structure, and we are actually envisioning that we make the structure, aircraft structure, which can generate the electricity while using it, like from the aircraft vibration, right? And as well as if there is some damages happening or about to start, it can detect or it can give the information that this structure is gonna uh, break or is about to fail. So
Yeah.
both we can do by this smart structure, and that I showed also that lightweight composite structure we are printing by the use of additive manufacturing. So we are trying to integrate composite structure with that flexoelectric sensor, which can be used in those applications.
Yeah. Thank you.
Thank
Yeah.
you so much.
Since we have a number of people still here, I'm going to stop recording. And then I think what would be very nice is if people, particularly who are doing master's, PhD, stuff like that,